in order to really understand weather, we need to talk about global convection currents and how they impact weather patterns and climates in different parts of Earth. So just to go back to the very basics, if we're looking at a map of Earth, near the equator, the sun heats Earth most intensely. So in this area, you're getting the most solar radiation per square foot compared to any other spot on Earth. As you travel up away from the equator, the radiation gets spread out over a larger surface area for the same amount of energy incident upon Earth, and so that energy is not as densely, it's not hitting Earth with the same amount of energy per space, and so it's not heating it as much. So the equator is the spot that gets heated the most intensely, which causes evaporation to be high from these areas, and the air is rising off the surface of Earth. This is what causes tropical rain showers, and we will talk about that in future slides. Okay, so what we saw on the last slide, if we just looked at that idea that the Earth is getting heated most intently at the equator and least intently at the poles, what you would expect to see is that heat is rising from the equators, traveling up to the poles, and getting cycled back down. So you would expect to see convection currents to just look like this, where along the surface of Earth you see air traveling from the poles down towards the equator, and then it gets heated and rises back up in the atmosphere, etc., and gets cycled. But that's not what we end up seeing, and there's a number of reasons for that, and that's because this system is much more complex than what we were looking at in that previous slide. So here's some things that add complexity to the system. First of all, Earth is rotating, so Earth is constantly rotating around, and as a result, these air currents are not going to just travel straight from the pole straight down to the equator. Also, Earth does not have an even distribution of land in the northern and southern hemispheres, and the land heats up more quickly than the oceans and cools down more quickly, and so that's going to cause differential heating over Earth's surface. So there's more land in the northern hemisphere than there is in the southern hemisphere, so that northern hemisphere is going to absorb more heat on the land surfaces. And then finally, we neglected in that last slide and in this picture on the slide to acknowledge the fact that Earth is on a tilt, which causes seasons. And so you're not going to get heating always at the equator predominantly because we are on a tilt. And so sometimes there are areas around the equatorial region that are going to be receiving more incident solar radiation. And that varies depending on the season. So we just said that Earth has seasons, and of course you've all experienced that, even if you live in somewhere like Arizona where we joke that it's always kind of summer here. We do have different times of year where there's more sunlight and more heat and less heat. So the seasons are caused by the tilt of Earth. The tilt on Earth is about 23.5 degrees. In geological time, that does change a little bit, so it's not always 23.5, but for now in our lifetimes it will be 23.5 degrees as compared to the plane in which it travels around the sun. So that's your perspective. So if we just look at North America, this little blob of land that we live on, if you're in Arizona or anywhere in the United States, or Mexico or Canada, we're all in North America. And so in North America in our winter, we are tilted away from the sun, and so in the winter we receive less hours of daylight. In the summer, North America is tilted towards the sun, and so it's receiving more hours of daylight than night, and so you're getting more than 12 hours of daylight during the summer part of the year. When we hit the equinox, so twice a year there's an equinox, and that happens in fall and spring, and that's a day in which both hemispheres are receiving equal amounts of daylight. So North America and South America, they're all receiving 12 hours of daylight on those equinox days. Okay, so we're going to pause here and start up on global convection currents part 2 in the next mini lecture.